This video looks at forcing objects from an object browser. It's often convenient or necessary to be able to change the value of an object while a logic program is running. Temporarily replacing the value of an object is what we call forcing. You may want to force an object to simulate a condition to test program operation, say during commissioning or while developing the logic, or to replace a measured value of a damaged sensor until you can replace that sensor, or to override a sensor value taken offline during maintenance actions. RemoteConnect offers forcing of all object types, so that includes I/O objects and objects that are not assigned to I/O. And this is where it occurs. So on any of the object browsers that you've created, and you simply select the forcing button here. So how is forcing different from writing an applied value to an object? We've done that already by entering an applied value and then selecting the write button. Well, forcing removes write access to the object. So after writing the forced value, that value cannot be changed by input hardware, by logic, or by a SCADA host or operator interface terminal. And forced values are retained. So if the RTU is rebooted or power cycled by a power outage, the retained values remain. There's also a red LED illuminated on the RTU when one or more objects is currently forced. Let's look at some examples now in RemoteConnect. We'll begin by creating a new project. And we'll select the default connection over USB. Now, for this project, I'd like to use an actual application to discuss forcing of I/O objects. So let's consider a tank or a reservoir that has a liquid in it, and this tank perhaps will have pressure generated in it. So for our digital input, we will likely have a pressure relief valve on the top of the tank. So I'm going to rename this digital input pressure 1 relief valve, and I'll give it a new object grouping name called tank 1. Now to keep this level under control in the tank, I'll have my first digital output be the pump 1 motor, and we'll also put it in the same object grouping. For analog inputs, let's begin with the pressure in the tank. And then the tank level. Same object grouping. I'll apply the changes. Now, forcing is done online, so we'll begin by going online, and we need to write these new object names to our controller. So we'll write the project. All right, so online is where forcing is done on the Objects tab from an object browser. Now I find this object browser, I can do forcing here for sure, but I find that my objects I'm concerned with are too far apart. So I'm going to create an object that just has these 4 objects in it, an object browser. So we do that back on the Configuration tab under Object Browsers. There's my default one, and this is where I'll add a new browser. I'll call this one Tank 1. And its entries will basically be all the objects that have my new group name, Tank 1. There they are, there's the 4. So now this new object browser should appear under online. There it is. And I can refresh this. Let's save this project now. All right, the first example for forcing, we're going to use our digital input. This is the relief valve on the top of our tank. Now let's say that this was chattering. So if I look at a 1 second update rate and we refresh continuously, let's say my relief valve was showing an obvious failure, was chattering back and forth, and I need to fix this. So to have relief from the chattering, I could force the relief valve to show that it's actually okay, that it's off. So let's try that. Well, to force, you normally double click the row, but to do that, you have to turn on forcing. To do that, you can't be in continuous update mode. So that's the first step. So now the button can be selected. We turn it on, and now double clicking this row, here are my forcing options for this object. I can force it to its current value, which is fine, that's 0, or I can force it to a specific value that I would enter. So 0 is fine, let's force it to that. Now it's refreshed. We see the marker here saying that it has been forced. And as we refresh or refresh continuously, if I alternate the value back and forth, it no longer shows the value of 1 because it's forced to this value. Now there's one other spot that I can look at forced values, and that's this dedicated object browser called forced objects. So if I refresh this one, this lists just the objects that are currently forced. So that's why we have this one here. You can also access the same forcing commands by turning them on this, this location. So if I turn it on here, and the interesting thing here is I get to see both the forced value and its actual value. So at the moment it's still, say, chattering back and forth, and I can see both values. The forced value is the one that the logic would see, or that a SCADA host that polls the RTU, it would see this value. So if I've just fixed the value, the switch that is, and it's now reading stable now at off, I am free to remove the forcing. So I can either clear it all or double click the actual object and clear it individually. And it refreshes to show that that's no longer forced. And if we go back to our tank object browser and refresh it, we'll see there the force is removed in the quality and the icon at the beginning. Our next example is an analog input, so we choose our pressure 1. Now I'd like to also follow from the logic editor what happens to the object while it's being forced. So we'll select configuration and open the logic editor. And in here I'll create a new animation table and add pressure 1. It's an object, so I select the value property. To see its value, I just need to connect, and there we have it. So as I vary the analog input, I'll see its value change. Okay, so the case I'd like to consider here is where we need to recalibrate this pressure sensor. And instead of having to remove the pressure sensor during the operation of the logic and see the value go to something like 0 or some other invalid value, I can force it to this current valid value while I take it offline to calibrate. So let's switch back to RemoteConnect, and online I'll force, I'll just refresh the current value. There it is. And I'll turn on forcing and then force to the current value. Let's see again back in logic. If I now vary the state of the value, I don't see it changing here at all. So that's what we wanted. But in RemoteConnect, I can look under forced objects, refresh here, and I'll see that the actual value, the one I'm calibrating, is still changing. So I can Let's say I've brought the value down to its lowest point for calibration, and then I might take it all the way up. To its high point. So throughout this, the forced value remains, and that's the one seen by the logic. After I'm finished calibrating, I return it back to service, and its value might be somewhere near where we left off. Here we are. Okay, so if I look back in logic at the moment, I still see the value 4138, but as soon as I remove forcing, and return to the object browser to refresh, there the icon's gone. It should now read a value around 5120. So if we return to logic, there it is, back to 5120. Let's review the interaction between the object database and the logic editor during forcing. Consider the SCADA pack as having the object database and the logic editor. There are I/O objects, system objects, and some user-created objects. For input hardware, their values are read and copied into the input objects. Then those values get loaded into the logic variables at the beginning of a logic scan. Logic executes. We may look at some of the objects in an animation table, and then variables will be written to the objects if they're output hardware or user objects at the end of the logic scan. So this is when the output hardware gets updated with the data from the output objects. So in our first example where we forced a digital input, we had a chattering digital input, and we decided to force the switch to off while we fixed the switch. So in this case, we've effectively removed write access of the input hardware to that object. For the analog input, we wanted to recalibrate the sensor, so we again removed write access. We used the current value and forced it so that logic would still see that value while we changed the analog input hardware. Looking at digital outputs now, we have our pump digital output. Now consider the case where the pump is controlled by tank level, perhaps in a lift station application. And maybe while monitoring, I've noticed that the tank level hasn't changed in quite some time, and I believe it might be stuck. So to override logic and confirm that, I could force the pump value and turn it on. This should change the level, and then I can validate whether the tank level sensor is jammed. So to do that, we go out of refresh mode, select forcing, and in this case, I want to change the value to a specified one, that being on. There, I just heard the relay click. And if we go over to logic, there's the value turned on here. Over to forced objects and refresh here. And note that for digital outputs and analog outputs, the source and the forced value are always the same. Since the source begins with the object, there's no hardware before that, and the resulting value goes out to hardware. I'm going to change the example slightly. First, I'm going to turn off the pump. And then I'm going to clear forcing. Now, in logic, I'm going to add a small program. And in this program, I'm going to set the pump off all the time. So I'll use a move block. And I'll write a 0 into the pump's value. Now we'll compile that. This is an online change, so it'll happen right away. All right, so there we see that the pump is off all the time, and indeed it is with the animation here. Let's see if the story is true. First of all, I'll write the source code because this was an online change. Okay, so yes, it is off. Now, what if I was to write true to it? What would happen here? So this is not forcing, it's just writing directly a on. I heard the click, but I see on the RTU that the output is indeed off. So it must have quickly wrote the on, and then the logic returned it to false. So there indeed it still is false. And when I refresh here, I see that yes, it is false. Okay, that makes sense. Let's use forcing instead. So now I'm going to write the pump on. I heard it click. I can see on my RTU that the output is indeed on, and when I refresh, it says it's on. What about in logic? Well, logic says it should still be off. Does this make sense? Well, let's return to our diagram we looked at earlier to see if we can make sense of this. So with output objects, they're loaded into the variables at the start of the scan. Logic executes if it's there, and then the variables are loaded back into the object and then written to hardware. So when we forced our digital output, loaded, wrote, there was no logic, so there was no write access, but in this case we still turned our output on. What happens when the logic is added? So here's our example here. We move a 0 or a false into that object. We see that it's true here, but because the forced value causes write access to be removed, the update of 0 is not written to the object, so the output hardware stays true. The same behavior will happen with analog outputs as well. Let's demonstrate that here. I'm going to add to this object browser my first analog output. In logic, I'm going to write a value directly to the analog output. And build this. Now I can add to our animation table and see there's the value 7500 as expected. I'll write the source code right now. Now first what we're going to do is write to the analog output directly and see what happens. So in this case I'll write a value of 2000. Actually, let's refresh first. And I see my 7500. What happens if I just try a direct write? Not a force, but a write. No, if I refresh, yeah, it's not effective. As we expect, the logic wins. The logic is overwriting with the 7500. Well, what about forcing? When we refresh, we see that, well, the forced value definitely wins. And if we go to our forced objects, we also see here that and remember I mentioned that both digital outputs and analog outputs, the source and the forced value are always the same. But in logic, yes, as we expected, the value will still show the value it tries to set within logic. Let's return to our diagram and see if this makes sense. So here we have our analog output object. It's loaded into the variables at the start of the logic scan. The logic writes 7500 into it, and then that value is updated back into the object, and that writes to hardware. Well, what happens when we force the value? When we force the value to 2000, the same value of 2000 is loaded into the logic variable at the start of the scan, but the logic then overwrites 7500. Now here's the case where it doesn't get updated. So because of forcing, write access has been denied, and the value remains at the forced value 2000, which ends up going out to hardware. This is the case even if a SCADA host or an operator interface terminal were to try and write to this object through a protocol. It also has write access removed so that the forced value remains the value that is written to the object hardware. I have two final use cases for forcing, and these will be for non-IO objects. So I'm going to add these user objects to the configuration tab, and this will be called level set point. I'm going to make it an integer and put it in the same object group. I'll add another object, and this will be level PID out. And I also want to see it as an integer in logic. So there's a change to the number of objects, so we have an update to the logic side. Now that we're here, what I want to do with these two new objects is add them to a PID block. Now there's various parameters in the PID block. I'm only going to enter a couple of them for this demonstration. So the set point will be my process value, and the out from the PID block will be my object here. Okay, now instead of completing the configuration here, I'm going to explain forcing to these two parameters from our diagram. Continuing with our application of the tank and its level, let's say the set point for that tank is determined by the SCADA host. The SCADA host writes the value of 70% to the RTU to set that set point. Now, if I was local to the RTU and I needed to override this set point for some emergency or some test point where I needed to change the level, I could force it locally, for example, to 63, and that value would be loaded directly into the logic and used to determine the output. So in this case, once again, the write access is blocked from the SCADA host and allowing me to override and set the value to the force value. In a similar case where we have the PID output, this is used to drive the pump through a level control drive, and it would be written by Modbus to the drive, and the output essentially is the drive speed in frequency. Now, again, if I wanted to locally force a different speed for that pump, I could do so by forcing the value and override what logic would normally write into the object, preventing write access and allowing me to apply the forced value directly to the drive. Forcing cannot be used to determine the pathway through your logic. Consider this example. I have a user object called speed. If it's forced to a value of 80, it still doesn't determine the resulting speed or the pathway through your logic. Well, why is that? Well, let's look at it. First, the speed object value is loaded into the logic variable at the start of the logic scan. But right away, the speed is recalculated to this value, 105, and then determines the course through your logic. So just having remove write access to this type of object won't determine the course of your logic. So whenever the value is calculated and then used again within logic, forcing cannot override that value. There is still a way that you can change the pathway through your logic for testing. It's called forcing for ebools. For those of you familiar with Unity Pro and the use of the ebool variable type, this is used for forcing Boolean actions. Now RemoteConnect does support this, but only the forcing action, not the edge triggered actions. These two buttons are what control ebools. For RemoteConnect objects, forcing is only done through the object browser. Let's look at an example of an ebool. I'll open up my elementary variables and I'll add a test Boolean here, and under type I'll select the ebool. I'll also add it to my animation table. Now usually to get the proper value here I do need to close and reopen that. Okay, and we also need to build. Okay, that's better. Now, if I want to modify this value, I can't just type in and modify it. I have to select the modify button. So this is where I could enter a 1 or a 0. Now, if I want to force the value, I select the force button and I select either force off or force up, force on. In this case, I'll force it off. The F0 is shown. Now, if we went over to RemoteConnect, we'll write the logic source first. But the same ebools, when they're forced, will also cause the red LED on the RTU to show the force case within the RTU. Also on the status tab, if we refresh this tab, we'll see that there are 2 active forced objects and 1 forced Boolean or ebool. Also, if you go over to the logic and refresh this, you'll see that there are also account for the number of forced ebool variables. So these two allow you to keep track of not only the forced objects, but also the forced ebool logic variables. Returning to the logic editor, we can also force the value on or remove the forcing. And then when we go back here and refresh, we'll see that the force value has been updated, and in logic, refresh, and the number of ebools has also been set back to 0.